The tech industry is currently trapped in a cycle of constant ranking. Every few weeks, a new artificial intelligence model enters the market, is subjected to tests, and takes its place on a crowded digital leaderboard. We tend to evaluate these systems like hardware components. We assume that superior scores on a technical specification sheet will naturally translate into superior performance in our daily work. If these rankings were absolute, an objectively better model would win every comparison and handle every task with consistent precision. Billions of dollars are being spent to climb these rankings, chasing small percentage gains on standardized benchmarks. However, this entire methodology misses the most unpredictable variable in the system, the person providing the instructions. Relying solely on benchmark scores to judge an AI creates a false sense of security regarding what the tool can actually do when it's in your hands. Many users have experienced the frustration of using a top-tier, highly ranked model only to have it return a generic or useless response to a simple prompt. If the system is an objective genius according to the data, why does it occasionally fail to handle basic instructions? The problem is that we are trying to measure dynamic, interactive systems using the same static metrics we use for a calculator. Researcher Salali Banerjee suggests that interacting with an LLM is more like managing a classroom of students than operating a machine. An LLM, or large language model, is an AI system trained on massive datasets to predict and generate human-like text. Different students arrive with varying baseline strengths, represented by nodes showing different natural aptitudes. No student stays at the top for every subject. High performance often drops when the focus switches. Even capable students require high-quality instruction to reach full potential. Otherwise, performance stagnates. An AI's underlying architecture defines its possibilities, but human guidance determines how those possibilities actually manifest in the real world. We can prove this divergence by running a single AI model to see how it reacts to different levels of instruction. In the first instance, we provide the model with a short, vague prompt that offers no context or specific goal. The resulting output is basic and uninspired, a direct consequence of poor teaching. Now we use the exact same model, but we apply specific context, clear constraints, and a structured framework. We assign the model a professional role, define its target audience, and set strict rules for the final format. This prompt forces the model toward an expert-level response, bypassing simple paths. This occurs within the model's latent space, a multidimensional mathematical map organizing relationships between concepts. The model doesn't look up an answer. It travels through this cloud to construct one. A human instructor provides the steering, navigating through this latent potential to reach a precise and sophisticated destination. The obsession with finding the best model through static debates is a distraction from the reality of how these tools evolve. The question we should be asking is, how well are we teaching the system? As different AI models reach a similar level of raw power, simply having access to the software will no longer provide a meaningful edge. The ceiling on what these models can achieve is no longer set solely by the engineers in Silicon Valley. The primary bottleneck for this technology is now the communication skills of the person sitting in that chair. The technology is ready. The challenge is whether you can transition from a passive user to an effective teacher for these systems.